Hello, my name is Joachim Pieprek, and I would like to present the simulation and analysis of gallium nitride-based bipolar cascade lasers exceeding 100% differential quantum efficiency. And I would like to thank my collaborators for providing all these experimental details. The group in Poland succeeded for the first time to fabricate a gallium nitride-based laser with actually two lasers separated by a tunnel junction. And this device is called cascade laser because the electrons are moving from the end side, from the bottom end side into the first quantum well, generate a photon, and then go through the tunnel junction to the second quantum well and generate another photon. So each electron theoretically could generate two photons. That means a quantum efficiency of 200%. The same is true for holes that come from the other side and meet the electrons in the quantum wells. So that's why it's a bipolar cascade laser. And as I said, 200% is theoretically possible, but in the measurement, we see slightly more than 100% only. So there are still significant losses and significant room for improvement of that design. And that was my motivation to do a simulation and study the internal physics of this unique device. And let's see. And I use the Pixel-D software by Crosslight to do these simulations. The software enables a self-consistent laser simulation combining drift diffusion, quantum well band structure and gain calculation, the optical model and the heat flux model self-consistently. And this, of course, is a very complex model, and I don't have time to go into details, but you can find more details at archive.org, where I uploaded a preprint of the paper that accompanies that presentation. Just look for my name and you will find that paper on archive.org. And I have to learn how to work with Zoom. So, and of course, this is not a plug and play software. You have to specify a lot of internal models and parameters for a successful simulation. And here I show the table with the layer structure, and the green layers are the tunnel junction, which are highly doped with magnesium and which cause the strongest internal absorption. So all these internal absorption parameters have to be set by the users, and luckily the group in Poland has already studied some of these absorption issues, so I could build on their work. And this strongly absorbing tunnel junction is located in between the two lasing modes, so where the optical intensity is almost zero, so it doesn't hurt much. But what my collaborators in Poland found out is that the InGaN waveguide layers do contribute a lot to the absorption because the band gap is close to the photon wavelengths, and due to the band tails that we have in alloys, there is significant absorption in these InGaN layers. So the absorption is given here on a logarithmic scale, and I will talk about this a little later more. And this is a band structure, an energy band diagram of the device. You see the electrons come in from the left-hand side in the conduction band, generate a photon by meeting holes in the quantum well, then continue through the tunnel junction back into the conduction band, generate another photon, and going out. And one of the most unique things with this laser design is the very thick quantum well, 25 nanometers thick quantum well. And that almost seems impossible because common wisdom for gallium nitride-based devices is that we need very thin quantum wells because the strong built-in polarization field separates electrons and holes. So if we want to generate photons, these two wave functions have to overlap, and that only happens in thin quantum wells. When we make the quantum well thicker, as you see here, photons and electron wave function are separated. But in a laser, you have enough carriers, you put a high enough current density into the device so that these bottom quantum wells fill up with carriers and are able to screen the polarization charge that is located at the interface of the quantum well. And that is what I show here in this self-consistent simulation. The screening is that good that we achieve flat band conditions in the center of that thick quantum well. That means the field is practically zero, and the second quantum level can then fill with carriers that show a very good overlap and generate the optical gain that drives the laser. So that is, in my view, one of the most unique features of this laser diode. And here is a simulated laser power in good agreement with the measurements shown as dots. It's the same measurements as shown here. And the simulation also shows that the top laser, which is slightly different in the design, turns on first, that we see this also in the measurement. And then the bottom laser turns on second, and the two powers add up to a total differential quantum efficiency of 112%. So it's not quite 200%, and the question is, why is it so low? And here we have to analyze losses, and the differential quantum efficiency is mainly limited by optical absorption of photons or by carrier leakage. So let's look at the optical absorption first, and the red line here shows the integrated modal absorption, so the product of local absorption and optical intensity, and you see the strongest increase in modal absorption happens inside these InGaN waveguide layers. All the other layers don't contribute much, so we have a total modal loss of 14 per centimeter, which is pretty high for a laser in general. And on the other hand, carrier leakage is shown in the simulation doesn't really matter. So we have here plotted the current density of electrons and holes. The electrons come from the left-hand side, go into the quantum well, and then very few electrons leak out, more than 4 orders of magnitude lower than the injected electron density, current density, and the same is true for holes. So there's very low carrier leakage, so the carrier leakage doesn't matter in this device. The next issue is total energy efficiency, also called power conversion efficiency, and that is simply the total lasing power divided by current times voltage. And in this simulation, it's only 18% for this laser. And the main reason for this low number is the strong bias that we see here, more than 12 volts at the highest current. And the main reason for that is the p-doped cladding layer of the laser. And that p-doping is pretty low, so the resistance is pretty high in this laser design, causing most of the bias. In this simulation, we assume an almost ideal channel junction using rectangular doping profiles. In real lasers, this is never rectangular because of dopant diffusion, but that is hard to predict in a simulation. So we somehow underestimate the bias in this simulation. So what can we do for bias reduction? There are two avenues, basically. First, we can reduce the thickness of the cladding layer, and that is shown here. With smaller cladding layer, the channel junction gets closer to the optical mode, to the lasing mode, and increasing overlap causes more absorption from the channel junction on both sides. Actually, in this optimization, we assume two identical lasers, so the bottom laser is the same and at the bottom and the top in this simulation to make it easier to understand the results. So the channel junction loss increases with lower thickness, that's to be expected, and the total modal loss increases as well. But the bias is decreased quite a bit, so that the ideal thickness in this case is 150 nanometer, which gives a slightly higher efficiency of 20%. So the second avenue is to increase the cladding doping. As I mentioned, the dopant is pretty low, which is part of the problem with this growth technology. 1 times 10 to the 18 magnesium acceptors means 1 times 10 to the 16 free holes, because due to the high acceptor activation energy. So we would like to have a higher doping, and as we do this, we can reduce the bias dramatically, and while the absorption is increased only a little bit. So the best optimum doping would be 15 times 10 to the 18, which gives 2 orders of magnitude less holes. Still not many holes, but this is the best we can do here. That gives 25% power conversion efficiency. And this design we use in the final simulation of CW operations that includes the self-heating. In practice, this has not been demonstrated yet. So all these laser measurements were done in pulsed operation, which reduces the heating. And of course, the goal is to also operate that in continuous wave operation. And the key parameter for such operation is the thermal resistance. The thermal resistance is the internal temperature increase divided by the total heat power. And from the literature, I got good numbers, or best numbers for the thermal resistance around 7 Kelvin per watt. So, and when we use this in the simulation, then the power is limited to about 1 watt output power, and then the internal heating is so strong that the gain reduction is relatively strong when you go to a higher temperature, which means that to maintain the threshold gain for lasing, we need higher and higher carrier density. And higher and higher carrier density means that we have more carrier losses. And one loss that rises most strongly is the Auger recombination that goes with the third power of the carrier density. And we see in this plot that as the current consumed by Auger recombination is even higher than the current going into the lasing. And that is the cause for the roll-off in this case. The other current contributions are much lower, at least by an order of magnitude. So we can say this, despite the large thickness, which reduces the carrier density in a quantum well, the Auger recombination remains the main problem in CW operation. So in summary, we have shown that the polarization field in this white quantum well is fully screened by low-level carriers, and the gain is mainly generated by higher quantum levels. The differential efficiency is more than 100%, but still strongly limited by internal absorption, not by leakage. And the power conversion efficiency suffers from the strong resistance of the p-Cladding layer, which can be reduced by higher p-doping of that layer, higher magnesium doping. But when it comes to CW operation, this is still strongly limited by Auger recombination, and from the simulation, it is recommended to set up a device with less than 7 Kelvin per watt total thermal resistance to achieve CW operation in real life. So all these results are written down in the preprint, and you can find that at archive.org when you look for my name. Thank you very much for your attention.